Hello everyone, welcome. This is Steve Suffoletto from the Flint Group from the Packaging Inks Division. Today's presentation is titled Instrumental Color Assessment. We're going to be talking about the pros and cons of instrument color assessment, densitometry versus colorimetry. We'll define L star, A star, B star color space, as well as L star, C star, H angle. We'll define total color difference, or delta E, where total is a sum of three independent parts and difference is a distance in color space. We'll determine pass-fail tolerance limits. We'll correlate between person and instrument. And we'll talk briefly about statistical concepts when making a decision. Instruments are very objective and they're very factual. They provide you with numbers that you can compare and do further analysis on. Unlike visual assessment, which is very subjective and opinionated, now you have to apply verbal word adjectives to what you see and what you think, and that might be a confusion when communicating. Instruments are very consistent and repeatable. You get the same results most of the time. And they don't get tired, they don't get bored, and they're not affected by psychological phenomena. However, they do have some disadvantages. One is, for small companies, they're still very expensive. And they're not practical for complex pictorial image scenes, pictures and photographs, color separations, because the aperture masks out the surround influences and the aperture masks out any adaptation effects. So for solid spot colors, they're great, but for color photographs, you have to understand how to use them. The instruments need to be verified and confirmed in terms of the hardware and software settings and conditions. You don't want to accidentally push the wrong button because that could change something that you're not aware of. You need to verify the calibration and the certification are current. Most instruments will do automatic self-calibration. Certification is typically done annually. You have to verify that the application of your intended use fits with the inter-instrument agreement and the gauge repeatability. The manufacturer has specifications on these. Let me give you an example. If you want to measure density, the GR&R says the general rule is 10% of your total measurement variation should not exceed your total tolerance. So if you're measuring density, SID, and your tolerance is plus or minus 0.05, your total tolerance is 0.1. So 10% of 0.1 would be 0.01. And surely your densitometer can measure to those precisions. However, if you're measuring delta E and your tolerance is 2, then 10% of 2 is 0.2, and 0.2 is getting close to the precision of the instrument and its inter-instrument agreement. So you have to be careful about that. The biggest problem I have with instruments is that some people blindly trust the numbers and forget to look. So you have to look at that sample under a magnifying glass to make sure you have good print quality with no defects. So the ink transfer and lay should be very smooth and uniform. No pinholing, no mottle. Your halftone dot structure should be not distorted or deformed, no doubling, no slurring. Your halftone dot should not have any centered hollow donuts. These are some of the manufacturers of spectrophotometers. X-Rite is the largest and most popular. Teshcon is number 2. Then we have Konica Minolta, Ahera, and Betacolor. Tobias makes densitometers. Cosar is no longer in business. Grade Tech Macbeth was purchased by X-Rite. Barberary, Viptronics. And I mentioned the other last two here, Variance and Nix, because they make small battery-operated portable spectrophotometers that are interfaced with smartphone apps using wireless Bluetooth communication. Let's talk more about the settings and conditions of your instrument. Well, depending on your sample, you want to make sure you use a 0.45 on smooth surfaces. A 2 millimeter aperture is fine for 133 or finer LPIs. You have your M condition. 0 is legacy or incandescent. M1 is daylight. M2 is daylight with UV cut filtration. And M3 is polarization. If you buy the exact XP model, M3 is not available. The illuminant can be D50 or D65. The graphic arts printing industry prefers D50. D65 is preferred by photography and computer graphics. You have the observer angle, 2 degree or 10 degree. graphic arts printing prefers 2 degree. The paint industry and the plastics industry prefers 10 degree. The backer, whether it be white, black, or self-backer, is important because if the substrate you're printing on is not thick in terms of caliper, it's not opaque, it's translucent. When it comes to films that are clear films, you have to make sure you have sufficient opaque white to give you good opacity. Now that you have all your settings and conditions set, we have to think about the calculations. Are you using the correct target aims? Are you using the correct delta E formula? Strongly recommended delta E 2000. But are you using the default suggested recommended LCH weights of 1 to 1 to 1? And finally, are you using the correct tolerance limits? So let's compare the instrument technology. Densitometers are basic, the least sophisticated. Spectrophotometers are the most advanced. The engine inside of a densitometer are 3 filters. We call them status T. They're Kodak Raton red 25, green 58, and blue 47. The filters inside the colorimeter are now going to try to match the color matching function of the human eye for vision. The engine inside of a spectrophotometer is typically 30 filters every 10 nanometers apart. A nanometer is 10 to the minus 9 billionth of a meter. Densitometers are the least expensive, around 3,000. Spectrophotometers are the most expensive, around 9,000. The application usage, densitometers are still very valid for process control, for measuring metrics like solid ink density and tone value increase. Colorimeters, their application are typically calibration, optimization, and building ICC profiles. Here we'll use LAB, LCH, and delta E. Spectrophotometry application would be CXF, color exchange format files, ink formulation, and metamerism or metameric. The metrics here are percent reflectance spectral data. ICC Max is now making ICC profiles not out of LAB data, but out of spectral data. Densitometers were popular in the 70s and 80s, still are. Colorimeters were popular in the 1990s, the 2000s, still are. And spectrophotometers were popular in 2010 and going forward. Let's compare densitometry and colorimetry. So the visual attributes are lighter and darker. With densitometry, that would be the density. Density is darkness, D for density, D for darkness. And that's done through the highest filter. Colorimetry, it would be L-star. Cleaner-Dirtier, that's grayness. And with a densitometer, that's the lowest divided by the highest filter. And then colorimetry, that's C-star. Colder and warmer, with densitometry, that's called hue error. That's the middle filter minus the lowest, divided by the highest filter minus the lowest. And then colorimetry, that would be the hue angle, the delta H, the A-star, and the B-star. I got some random chips here. It looks like they're chaotic. What I want to try to do is bring some logical structure and order to these. I want to put them into groups, categories, and classifications. So what most people will do is they'll say, some of these chips are all neutral. So let's take the neutral chips and put them in order, rank them from lightest to darkest. And when you do that, you get the tone scale. So the tone scale goes from white to black. White is 0% dot, paper, substrate. Black is 100% solid, and halfway between 0 and 100, or white and black, is 50% mid-tone gray. Then you can have quarter tone 25% and three-quarter tone 75%. Notice that density and L-star are opposites. They have a indirect inverse relationship, meaning as you go from white to black, density goes from low to high, but with L-star, black is 0 and 100 is white. So they go in different directions. Then you said to yourself, some of these chips all have the same hue. I'm going to pull all those out and try to rank those. So you rank those from gray to increasing colorfulness. We call that purity, saturation, chroma. So there we go from lowest chroma to highest chroma. With a densitometer, these probably would measure all about the same. Again, density doesn't measure color. Density only measures darkness. And in theory, these are all the same value or lightness, darkness. They're just difference in their chromaticity. And then we have hue, cold and warm. That's the H angle. So if you take white light and pass it through a glass prism, you get the spectrum or the rainbow out. And you can put those in the Roy G. Biv order. So you start off with red, then you go to orange and yellow, green, cyan, and blue. Now what's interesting here is there is no magenta in the spectrum of the rainbow because magenta is the combination or the mixture of red and blue. So if you take this linear line and wrap it around into a color wheel color circle where the two meet and mix, that's where you get magenta. All right, let's have correlation metrics here. Again, when you look with vision and speak with verbal word adjectives, you're trying to classify and categorize the accuracy of the color match. You're either same, close, or different. That attribute would be acceptability, and the metric would be delta E. That's often supplied by the customer in terms of their specifications. Lighter and darker is the value. That's the L star. It's the least important. It can fluctuate and vary the most. Cleaner and dirtier is the chroma or C star. That's in the middle. And then you have colder and warmer in terms of the hue, which is H angle, and that's the most important. People notice hue shifts quickest, especially in neutral gray colors. That's why neutral is used for gray balance. All right, let's define C lab, L star, A star, B star. Well, it's 3 dimensions. They're independent. We'll use Euclidean geometry or the Cartesian coordinate system for them. They're the opponent theory. That means either or. They can't simultaneously be the same. So the L star goes from 0, which is black, to 100, which is white. Those are the maximum values, by the way, minimum and maximum. And then you have the center origin at the intersection. This is 0, 0. And these are where the neutrals reside, your gray balance figures. So when your A is plus, you're magenta red. When you're opposite of that, minus A, you're green. When B is plus, you're yellow. Opposite from that, you're minus B, you're blue. So that's your C-lab space. Now, whatever you see, you should be able to think about its numerical value. And whatever the numerical value is, you should try to be able to visualize what it looks like. So here I have a standard of reference, a target and aim. It's a dark red, maybe a burgundy. And what I want to do is I want to change its color in 6 directions by 5 magnitude units, the input. So we can change the L star by plus or minus 5 units. Think of that as density dot or delta E. So this is lighter, that's darker. We can change the A star plus or minus. This is redder, cleaner. This is greener, dirtier. We can change the B star plus or minus. This is yellower, a hue shift. And this is bluer, a hue shift. So whenever you have a color, it has 6 dimensions. So its tolerances have to be 3 dimensions in 2 directions. 3 times 2 would be 6. So either you're lighter or you're darker, or you're redder or greener, cleaner, dirtier, or you're yellower or you're bluer, you're warmer or you're colder. And sometimes you have to think backwards or opposite or complementary. So if you don't see this yellower, think of it as being less blue. If you don't see this bluer, think of it as being less yellower. And this is a nice visual. You can get this from Pantone or Munsell, and it shows you the standard reference target aim with the change in A star and the change in B star and the change in L star. Now let's move on to LCH. It's still the same 3-dimensional space using LAB. The L star is identical, but now we're going to use polar geometry where we have a C star, which is a radius line. So once you have a radius line and A and B are perpendicular, you form a right triangle. That right triangle now has a hypotenuse, which can be used the Pythagorean theorem. C star is the square root of A squared plus B squared. And then we also have the hue angle. So the hue angle is the rotation around the color wheel or color circle, which is the circumference. So if you start at the right-hand side plus A, 0 degrees, going 90 degrees is yellow, another 90 to 180 is green, another 90 to 270 is blue, and another 90 is back to 360. L star, black, white, chroma, it's a radius line, and hue angle, circumference. All right, always use LCH because it's intuitive. It's how you see, it's how you think, it's how you talk about color. Lighter or darker, L star. Cleaner or dirtier, C star. Colder or warmer, hue angle. And if you want more specific information about the hue angle, then you would go to the B and the A, because minus B is blue and minus A is green. Blue plus green is cyan. These are all cold colors. And then you can go to B, plus B is yellow and plus A is magenta. Yellow plus magenta is red or orange. These are all warm colors. And again, you might need to be able to use the reverse opposite logic if needed. If it's not more, then it's less. 2 out of 3, this is from Munsell, hue, value, and chroma. Chroma is limited at the top because it has a maximum ceiling it can't go beyond, and it's limited at the bottom because it has a minimum floor it can't go below. The maximum C star varies with the hue, and it's typically near the middle in terms of L star. So in theory, any horizontal row here is going to be the same density because its value is the same, and value is close to L star or density. And density is colorblind. Density is darkness. Density is not color. And people often confuse L star with C star. So now that we know what LAB color space is, and now that we know what LCH color space is, let's take that color space and find out what delta E is. A line, you're only one dimension. That line has a length and a direction. It's a vector. And the length is calculated, the delta or difference in that length is calculated by the beginning start versus the finish end. If you take a square, it's two-dimensional. It's a flat plane. It's a slice. It has an area. Area is length times width. And the distance calculation is the square root of delta x squared plus delta y squared. If you take a cube, which is three-dimensional, it's a solid, it has volume. And volume is length times width times height, or volume is the area times the height. And its distance formula is the square root of delta x squared plus delta y squared plus delta z squared. Okay, now that we got all the math out of the way, let's come over to this diagram and let's look at this three-dimensional cube. It has a width left to right. We can call that x or a star. It has a length front to back, depth. We can call that y or b star. And it has a height bottom down, top up. We can call that z or L star. So if I put a point there, I call that the standard, the reference, the aim, or the target, and I put another point there, that could be a sample, batch, or lot, you probably want to know the difference between those two colors. The farther apart they are, the more different they are. The closer together, the more similar they are. So that difference is a distance measurement. So shortest distance between 2 points is a straight line, and that's how a bird or a crow would fly, the shortest distance. Well, we're driving on a road, so we can only make left or right turns. We can only go north, south, east, west. So we have to go that distance and length, make a perpendicular turn, and go this distance in width, make another perpendicular turn, and go that distance in height. When we do that, we realize we just formed a right triangle, 90 degrees, and this right triangle has a hypotenuse, which is the Pythagorean theorem. Color space in LAB is rectangular or square, but delta E is a sphere or circular. Then there's going to be portions where you have error, and this is a circle instead of a square is 21% error in the red. If you flip-flop it and try to put the square inside the circle, now you have 36% error, the red portion. Well, if you change the rectangle and rotate it on a diagonal, and now you try to fit a ellipse inside there, you still have an error, 32%. What I'm trying to suggest to you is that the delta E formula has been modified and altered over the years since 1930 to get better and better and better. A word of caution on delta E. Delta E is mononumerosis. It sounds like an illness or a disease. Mono meaning one, numerosis meaning number. Color is three-dimensional, trichromacy, trichromatic, triplets. you need 3 numbers to fully, completely describe a color or a difference. Those 3 numbers could be RGB, red, green, blue, additive. They could be CMY, cyan, magenta, yellow, subtractive. They could be XYZ, tristimulus values. Or they could be LAB, LCH, colorimetrics. Delta E is a single number, mono again. It's assumed to be equally distributed evenly by an average. It only has magnitude. It does not have direction. There is no plus or minus. So be careful. It often doubles when you change the direction. Near neutrals, when you get close to that origin intersection, the tolerance becomes a sphere or a circle. And as you increase outward in chroma, go farther out, that shape changes into an ellipse or an ellipsoid. The major axis of that ellipse is parallel to the chroma radius, the chroma hue. And delta E2000 is trying to mathematically compensate for the non-uniform LAB color space that was noted by both Munsell and McAdams. So these McAdam ellipses will change their size, shape, and orientation based on where they are in color space. And that's exactly what delta E2000 is trying to do, make that compensation. Now, we've talked about this before. When you look at 2 colors and you're trying to classify and categorize the accuracy of the color match, you use these word adjectives. They're same, they're close, or they're different. Now, for spot color, which is very simple, it's just a solid, you can use these tolerances. But for process color, because it's more complex, there's 4 independent, mutually exclusive variables, the cyan, the magenta, the yellow, the black. You have to have wider tolerances. Now, in the marketplace, there's different quality levels. So I would classify sheet-fed offset lithography printing folding cartons for the pharmaceutical or the cosmetics industry to be very high. Same would be a delta E of less than 1, close would be a delta E between 1 and 2, and different would be a delta E greater than 2. If your marketplace is medium, perhaps labels or flexible packaging, you might use these. And if your marketplace is low, commercial printing, publication printing, newspaper printing, periodicals, magazines, etc., you might use these tolerances. The point I'm making is different markets with different customer requirements and expectations require different tolerances. And the tighter the tolerances become, the more expensive it is to manufacture that product because it takes more time, labor, it takes more materials, ink and paper or substrate. You have to be more careful, you have to pay more attention, it takes more effort. Now, how do you determine your pass-fail tolerance limits? Well, we are currently doing a test. I've selected 16 judges, mostly press operators, supervisors, and quality people, ink technicians. We've looked at 28 samples that were produced over a year, 4 different SKU items, 28 different color OK jobs, all for 3M red. And what we have in this graph here is on the x-axis, this is the delta E going from low to high, and this is the y-axis, which is a cumulative percentage. We often call this the cumulative relative frequency, or CRF. Now this red plot, this red curve, is the fail data. Just think about this logically. If the delta E is low, you should have no fails. If the delta E is high, you should have a lot of fails. People don't disagree when things are the same. People don't disagree when things are different. People disagree in this area here. So as the delta E color difference increases, there will be more confusion about the pass-fail, and the fail rate goes up as the delta E goes up. That just makes sense, right? Low, again, low delta E's, low failures, high delta E's, high failures. So at 50% probability, you're going to fail at a delta E of 1.5. At a 90% probability, you're going to fail at a delta E of 2.4. Now, let's compare detect versus accept. Detect means you can see it, it's perceptible, it's noticeable. The minimum is called just noticeable difference, or JND, and it's typically a delta E of 1. Accept means that you approve it, you will okay it, you'll sign off on it, you'll pass it, you'll run that color. Acceptability is a functional fit for use characteristic. Most people ask, unfortunately, for what they want, not for what they really need. Acceptability depends on many factors. Now, some of these are external factors, the customer, their expectations, their requirements, their products, their marketplace. But many of these factors are internal when it comes to productivity, efficiency, profitability, how much time have we spent on it, how much material have we wasted on it, how late is the job, how many recent customer complaints or rejections have we had, those types of factors. Let me ask you a question. If we have detect and we have accept, then what is the relationship between them? Is detectability less than acceptability? Is detectability the same or equal to acceptability? Or is detectability more than, greater than acceptability? Well, it's not the same. It's not more. It's got to be less. So detectability is less than acceptability, or, saying this a different way, backwards, reverse, opposite, complement, acceptability has to be more than, greater than detectability. Okay, so let's compare the person with the machine. Visually, I'm asking you, how does it look? Instrumentally, I'm asking you, what are the numbers? You can pass or fail visually, and you can pass and fail instrumentally with the delta E. If you pass visually and you pass with instrument, everybody's happy. There's agreement. If you fail visually and you fail with the instrument with the delta E, again, we have agreement. So you should be happy. You're not happy that you're failing, but you're happy that you have agreement. So there's 4 possibilities here. 2 of them are in agreement. 2 of them are in disagreement. So if you visually pass, but you fail with the instrument, you just made a mistake, an error, there's disagreement. If you visually fail, but you pass with the instrument, again, you made a mistake, there's an error, there's disagreement. Now, the facial expressions here, we can talk more about confusion versus anger. So let's try to resolve the conflict here. You obviously have an error, a mistake, or a disagreement present. Who, person, or what machine is right or wrong? Who or what do you trust, have confidence in, and is reliable? Is it me? Is it you? Is it me? Is it it? Most people typically think it's them. They're always right. Human error versus machine error. So do you remember the movie 2001 Space Odyssey and the supercomputer HAL 9000? He always said he was always right. He was perfect. Well, was he? So which mistake or error is worse to make? So please be patient for a minute here. I think this is important. I have an obligation and responsibility to at least introduce you and share this concept with you. In inferential statistics, there's 2 types of errors or risks. They have specific names and meanings, definitions. We have type 1 and type 2 errors. We have alpha and beta risks. A type 1 error or an alpha risk is a producer risk. It's rejecting the truth. It's not as serious as a type 2 error or a beta risk, which is the consumer buyer risk, which is accepting false, so it's more important. Both errors and risks can be minimized by having a larger sample size, and capital uppercase N is the abbreviation or symbol for sample size. The application statistically here is for hypothesis testing. For example, medical clinical trials. I'm thinking about the recent COVID pandemic, where we tried to test vaccines to see if the vaccine gave you the same result or a different result, and if the different result was better or worse. So we had this control called a placebo, and we randomized the trial, and we did double blind, meaning both the person taking the test and the person evaluating the test didn't know what the right answer was. So let's get more specific to our industry application here. When it comes to quality control and quality assurance, we have acceptance sampling. Today, it's now called ANSI for the American National Standards Institute, or ASQ for the American Society for Quality. Currently, it's a standard in ISO called 2859. All right, here's the detail. If I have a batch or a lot size between 10,000 and 35,000, it tells me to pick 125 samples. If I find 6 defective samples, I need to reject the entire lot or batch. Now, the percentages are very, very small, but it's accurate because you're using the power of statistics. So the reason why I mention this is because management makes decisions. And you make those decisions about truth, reality, and fact. You then think, decide, and act about that. So if we use the example of criminal law, the judicial system with the judge and the jury, if the person's innocent and we say they're guilty, we've just made a mistake. If the person is guilty but we say they're innocent, we've just made a mistake. We want to minimize the worst types of mistake. So again, when it comes to making decisions in management, I don't want you to arbitrarily, randomly flip a coin and 50% of the time you say this, pass or fail. That's not how we run a business. That's not how we make decisions. We make decisions based on data, and you want complete, accurate, timely data. Your decisions are often only as good as your data. So we're back to this pass-fail for visual and instrument. Again, we have these two types of mistakes and errors. Now, the Delta E 2000 formula has been modified 4 or 5 times since the 1930s, and it's at a current state of 95% accurate. So is that 95% accuracy enough, good enough, close enough? The ultimate decider here is the human eye, vision. So you should look first before you measure. If you don't, then your judgment will be biased by knowing the numbers ahead of time. It's like guessing someone's weight after they step on a scale. You should confirm and verify measurements by looking. So the instrumentation and the math logic calculations of the Delta E formula are trying to model human perception. Munsell and McAdam ellipses are used to model. In closing, there are strengths and weaknesses to both visual and instrument assessment. The visual was in a previous part 1 video. The instrument is in this part 2 video. Instrument measurement should have a strong correlation to visual assessment. The current Delta E 2000 formula is about 95% accurate. Is that good enough, close enough? Most customers don't have spectrophotometers, so they're not going to be measuring our product. They're going to be looking at our product. They'll determine pass-fail acceptability based on vision. Vision is the ultimate gold standard in instrumentation. Again, based on Munsell and McAdam ellipses. And acceptability must always be greater than detectability. Here's 6 review questions you can look at your leisure. Thank you very much for your time and your attention. I hope you found this presentation interesting and informative. Please provide feedback with either comments or questions. And if you have time, like the video. Until we meet again, have a good day. Bye now.